Let's talk about the concept of the inner product integral. This will be our first foray into converting signals from the time domain to the frequency domain. So our overall goal is to take a signal x of t and convert it into some sort of equivalent expression which we'll call x of f for the time being, for lack of a better word. So x of t is the time representation, x of f is the frequency representation. Now, as we learned before, cosines, each cosine contains a single frequency. And therefore, if our goal is to convert x into a frequency representation, really what we're asking ourselves to do is to take x and convert it into a sum of cosines. Okay, so an equivalent thing is, can we take x and express it as a bunch of cosines? And if we can do that, then that's essentially the frequency representation, because each cosine is one frequency. Now, as we learned earlier, an equivalent representation to a cosine is a complex exponential. So one more equivalency would be to take x of t and express it as a bunch of complex exponentials. And again, if you can express your signal as a sum of complex exponentials, then that's essentially the frequency definition of it. So, as we learned, your complex exponential has the form ae to the j omega t, where omega is some frequency and a is a complex number. So, it turns out that there is a relatively straightforward function we can use to derive this. So suppose we have, let's say, given some periodic signal x of t. So for right now, we're going to restrict our conversation to instances where x of t is periodic, okay, with some period t. So what you can imagine is, I'm going to take some periodic signal, which I guess for now I'll just mock that up with a square wave, and I'm going to pass it into this magical box, and the box is going to allow us to ask, hey, does this signal x of t contain any energy at frequency omega? Okay, does this signal contain any energy at frequency omega? And what will come out of this box is the complex number a, okay, and it will tell us whether or not there is any energy at that frequency. Now, if there is no energy at frequency omega, our box will spit out a equals 0, and if there's a lot of energy at that frequency, then our box will spit out some value of a that has a large magnitude. So that's how I want you to conceptualize this, is that what we're doing is building a box that lets us say, is there any energy at this frequency? And the formula that does that goes as follows. So here's what's inside the box. It's what's called the inner product integral, and it works like this. Its definition for periodic signals is that a equals 1 divided by t times the integral over one complete period, and I'm just going to do integral sub t here, and I'll come back to that in a moment. And then it's x of t times e to the minus j omega t dt. So again, let's talk about the individual pieces of this. X of t, that's just the signal that we're trying to investigate. Omega is the frequency that we want to see if our signal has any energy at that frequency. And then we're going to multiply those together and then integrate it over one complete period. And that's a little bit interesting, right? So one complete period means we could integrate, so let's say this is one complete period, or alternately we could say something like this is a complete period. It really doesn't matter where we start and where we stop, as long as we integrate over a full full 1 period's worth of duration. And in coming videos, we're going to learn how to exploit that. We're going to be able to pick out limits of integration a little bit smartly that make the math a little easier. But that's the basic idea. In the next videos, we'll look at some examples of how to apply this integral.